Welcome to the Deep Dive. Today we're tackling a really interesting paper that's been making waves, Gaussian Mixture Flow Matching, or GMFlow. We've got the paper and we're going to really unpack what it's doing.
Yeah, absolutely. I mean, we've seen generative models, especially for images and video, come so far with diffusion and flow matching, but they do have their issues.
Yeah.
And GMFlow seems to offer some pretty clever ways around those bottlenecks. The results look, well, very promising.
Okay, so let's set the scene a bit. Everyone listening probably knows this, but just quickly. Diffusion models learn by adding noise and then reversing it. Flow matching learns the direct path from noise to data.
Exactly. Diffusion is like learning to undo the noise step by step. Flow matching learns the velocity, the direction, and speed to get from noise straight to the image. Both super powerful.
But not perfect. What were the main limitations GMFlow wanted to fix?
Well, two big ones, really. Sampling speed is a major one. Standard diffusion and flow models, they often need, dozens, maybe hundreds of steps to get really sharp results.
Which is slow.
Very slow. And that's partly because they usually approximate the denoising step with just a single Gaussian distribution. It's an approximation that, well, it breaks down if you try to take big steps. You get errors, blurriness.
Okay, so slow sampling. And the paper also mentions problems with classifier-free guidance, CFG.
Right, CFG. It's great for making conditional generation better, like generating a specific cat from a prompt. It works by kind of amplifying the conditioned signal.
Quite.
But it can sometimes push things too far. It extrapolates, and sometimes that extrapolation goes, well, out of distribution, ODE. That's where you get those weird, super saturated colors or other artifacts.
Gotcha. So slow sampling and weird CFG artifacts. That's what GMFlow is targeting. Okay, for our quick summary, the first minute gist, what's the core idea?
The absolute core is predicting a mixture of Gaussians for that flow velocity, not just a single mean value. Think of it as seeing multiple possible ways to denoise, not just one average path.
So richer representation of the possibilities.
Exactly. And because it's a richer, more accurate representation, they can derive new sampling methods.
The SDE and GMOD Solvers mentioned in the paper.
Precisely. These solvers can take bigger, more accurate steps, faster sampling, better quality.
And for the CFG problem?
They introduce probabilistic guidance. Instead of just extrapolating, they reweight the predicted Gaussian mixture using a Gaussian mask. It's a much more controlled way to apply the guidance.
Keeping things within bounds, basically.
Yeah, it avoids pushing samples into those weird ODE zones, reducing that oversaturation problem.
Okay, so quick recap. GMFlow uses Gaussian mixtures for velocity, gets faster sampling via new GMSD Solvers, and uses probabilistic guidance for better conditional results without the saturation issues. And the paper shows it beats flow matching baselines on quality, especially precision, with way fewer steps. Hits state-of-the-art precision on ImageNet 256 in just a handful of steps.
That's the high-level picture, and today our mission is to get into the weeds. How does it work? Why does it work? What does it mean for folks building these models?
All right, let's dig into that background more. You mentioned diffusion adds noise, then reverses it. Can you walk us through that forward process again and how flow matching differs?
Sure. So diffusion starts with clean data, an image, say. Over time, controlled by a noise schedule, alpha, sigma, you add more and more noise.
Gradually degrading it.
Right. Until at the end, time t, it's basically just Gaussian noise. Mathematically, it's like convolving the original image XE with a progressively wider Gaussian kernel to get des.
Okay. And the standard reverse process.
The standard reverse, like in DDPM, learns to go backwards. From pure noise at t, predict a slightly less noisy xt, then predict xt2, and so on, back to a clean sample at time 0.
Step-by-step denoising.
Yes, and crucially, each reverse step, that transition from x to xt, is typically approximated as a Gaussian. The model learns the mean of that Gaussian.
Okay, got it. And flow matching, where's the split?
Flow matching, it skips learning those intermediate reverse steps. It directly learns the velocity field. Think of it as a vector field that tells you, for any noisy point x, exactly how to move to transform it smoothly into a data point at t0.
More direct.
Yeah. They often use a linear noise schedule, makes the math cleaner. The optimal velocity turns out to be the average of this random velocity u, which is defined as xto0 sigma. You average that overall possible original data points at 0 that could have led to your current noisy 0.
So it learns the mapping from noise to data by figuring out the average correct direction based on potential source images.
Exactly. And it's usually trained with a simple L2 loss make the predicted velocity match that ideal average velocity. Then you generate by starting with noise and following the learned velocity field using an ODE solver.
And the problems slow sampling, CFG issues, they come back to that single Gaussian approximation in diffusion, or the difficulty of learning that complex velocity field perfectly in flow matching.
Pretty much. That single Gaussian is a bottleneck for diffusion sampling speed. And learning a single perfect velocity field for flow matching is hard, needs lots of small integration steps. And CFG, as we said, just extrapolates, sometimes too aggressively.
Okay, brings us to GMFlow's core. Using Gaussian mixtures for that velocity, how do they set that up? What's the loss?
Right, so instead of one velocity vector, GMFlow predicts a whole distribution of possible velocities, modeled as a Gaussian mixture. So Cooksed is a sum k components, each a Gaussian with its own weight ACK, mean EK, and covariance ACK.
K components, okay?
Yeah,
right.
And all those parameters, ACK, CUC, are output by a neural network that sees the noisy input X. The weights ACK use a softmax, so they sum to 1, like probabilities.
So for any noisy pixel, the model outputs not just one way back, but a whole set of possibilities, each with a probability and its own mean and variance.
That's a great way to put it. And the training isn't just L2 loss anymore. It's about making the predicted mixture distribution match the true distribution of possible velocities.
How do they measure that match?
Using KL divergence. The ideal loss minimizes the KL divergence between the predicted mixture and the true velocity distribution. In practice, since you don't know peaks directly, the loss becomes the negative log likelihood of the ground truth velocity x0 equals x70, averaged over data and time, under the predicted Gaussian mixture key.
Why Gaussian mixture specifically? What's the magic there?
Several things. First, a really important theoretical result, they prove theorem 3.1 about mean alignment. Even if the true velocity distribution is super complex, minimizing their KL loss guarantees that the mean of their predicted mixture converges to the mean of the true velocity distribution.
That sounds pretty solid. What else?
Analytic tractability is huge. You can calculate things like the mean, moments, and crucially the reverse SDE transitions, all in closed form. Makes designing good samplers much easier. And finally, expressiveness. Mixtures can approximate much more complex multimodal distributions than a single Gaussian ever could.
Okay. Now, they simplify the covariances down to just be Saussane-scaled identity matrices. Doesn't that limit things?
It's a simplification, mainly for computational efficiency and stability. Full covariances are messy. The authors argue that for predicting the mean velocity accurately, which the theorem shows is key, this simplification might not hurt much. The mixture structure itself, with multiple means off and weights ACK, captures most of the complexity. The shared scalar variance soft gives some flexibility.
So it's a practical trade-off.
Seems like it, yeah. And it doesn't seem to cripple the model's ability to learn the important stuff.
It's cool how it generalizes older methods too. K1S1 gives you back vanilla flow matching, basically.
Exactly. With one component and unit variance, the KL loss becomes essentially the L2 loss. And they even draw a line to categorical diffusion. If you think of the means mech as pointing to discrete tokens, and lets it go to 0, the weights ACK become probabilities over tokens. It's quite neat.
And this reparameterization they talk about, from the velocity distribution to an X-dish distribution. Breaking a leg.
Yeah, that's super useful. You just plug the definition of U back into the mixture formula for it, and you get an implied distribution over the original data, X0, given the noisy X. And guess what?
It's also a Gaussian mixture.
It is. Also a GM. This X view is helpful because 1, it's an estimate of the clean data. 2, it's what you need to derive the SDE reverse transitions analytically. And 3, it's the basis for their probabilistic guidance.
Okay, perfect transition. Probabilistic guidance. How does it fix the CFG oversaturation?
So remember, a vanilla CFG just kind of linearly pushes between the conditional and unconditional predictions. GMFlow instead takes its predicted conditional mixture, const C, and reweights its probability density using a special Gaussian mask function.
A mask?
Yeah, a mask. The new reweighted distribution cobu is proportional to the original conditional mixture times this mask. They normalize it, and crucially, if you start with a GM, you still have a GM after reweighting. You can calculate the new parameters analytically.
So instead of just shifting the mean like CFG, it reshapes the whole probability landscape. How is the mask designed?
It's clever. They create single Gaussian surrogates that match the mean and variance of the full conditional and unconditional GMs. The mask is then built from these surrogates. Its formula looks a bit complex, involving a guidance scale and the difference between the surrogate means.
But the core idea.
The core idea is to use these simpler Gaussians to define a mask that gently guides the original complex conditional mixture. It adjusts the mean and variance based on the guidance scale, but does so in a way that respects the bounds of the original conditional distribution.
So it doesn't extrapolate wildly like CFG can.
Exactly. It keeps things within the learned manifold, preserving the multimodal structure of the original mixture while still applying guidance. Less risk of ODE samples, less oversaturation.
Seems much more principled.
Huh.
Okay, let's talk solvers. The SDE and GMOD Solvers. How do they exploit the mixture prediction?
This is where the analytic tractability really pays off. For the SDE solver, because they predict the X-year base mixture, class XX, they can analytically derive the exact reverse transition distribution, CAS.
The probability of going from the current noisy state back one step.
Yes, and it's also a Gaussian mixture. So instead of approximating that reverse step with a single Gaussian like usual, they have a much more accurate multimodal distribution to sample from.
Which means bigger steps are possible.
Theoretically, yes. If their predicted core XU was perfect, one step of GMSDE would have 0 error. In reality, it's not perfect, but it's good enough to allow much larger steps, meaning faster sampling. They also mention an alternative way to implement it. Sample an XD from the predicted mixture first, then sample XT from PSTT, which is just a standard Gaussian. Apparently that can be more stable sometimes.
Interesting. And the GMODE solver, deterministic sampling.
So you could just use the mean of the predicted GM velocity in a standard ODE solver, but GMFlow allows something cooler, sub-step integration without extra network calls.
How does that work?
Given the predicted mixture at time t, Tor and XD, they have an analytic formula to estimate what the mixture would look like at any intermediate time between t and t. Let's call it QX.
Also a GM.
Also a GM. So they can effectively peek ahead along the flow path analytically. This lets the GMODE solver take multiple small Euler steps within one larger 8-step, using the analytically derived velocity at those intermediate points without needing to run the big neural net again and again.
Very efficient.
Right.
Reduces error without much extra compute.
Exactly. It helps fight the discretization error you get with large ODE steps. They do still need multiple actual network evaluations over the whole generation process, but the sub-stepping helps within each major step.
They also mentioned second-order multi-step solvers like Adams-Bashforth, but for GMs.
Yeah, similar idea. Standard multi-step solvers extrapolate the predicted mean from the last couple of steps. The GM versions extrapolate the entire Gaussian mixture prediction.
Okay.
They take the GM predictions from, say, time C in an earlier step. They transport the earlier prediction forward to time analytically. Then they look at the difference between the two GMs at time C and use that difference to extrapolate what the GM should look like at the next step, using a reweighting scheme similar to probabilistic guidance.
Wow, okay. Leveraging those analytic properties everywhere. Now, practically, for images high dimensions, pixel-wise factorization and spatial sampling, why these?
Right. Modeling a full GM across a whole 2.5 by 2.5v6 image at once, forget it. Too complex, too prone to mode collapse. So pixel-wise factorization is pretty standard. Treat each pixel's velocity, or latent variables, as an independent, low-dimensional GM. The total loss is just the sum of losses over all pixels.
Makes sense computationally, but doesn't that ignore spatial structure? Pixels aren't independent.
Exactly the problem. And that's where spectral sampling comes in to fix it. The basic GMSDE treats pixels independently, which can lead to spatially incoherent noise patterns. Spectral sampling generates spatially correlated noise first. It generates a random field in the frequency domain shaped by a learnable power spectrum that captures typical image frequencies. Then it uses something called Noether-Rosenblatt transport to map the independent per pixel Gaussian samples from the GMSDE onto samples from this correlated field. It basically injects the right spatial correlations back in.
Clever. And the transition loss, what's that for?
Stability, mainly. They found the standard KL loss could sometimes be unstable, especially if the predicted variance got too small. The transition loss is a modified loss based on those analytic transition distributions, but over a shorter time step, below low is less than 1.
How does that help?
Using 1 effectively puts a lower bound on the variance of that short transition. It smooths the loss landscape, stops the model getting too confident and unstable.
Okay, let's talk results. The 2D checkerboard tests first. What did they show?
Those were really illuminating. They showed GMFlow, especially with their second-order solvers, could capture that tricky multi-modal checkerboard shape with way fewer steps, like 4 steps sometimes, compared to baselines needing 8, 16, even 32 steps.
And the sample distribution.
Much better. Vanilla solvers often clumped samples in the middle or pushed them too far out. GMFlow samples were much more uniformly spread across the checkerboard squares, matching the true distribution better.
Did the number of components K matter?
Yes. Increasing K generally made the generated checkerboards sharper, especially with few steps. And they showed K1 with GMSDE was basically like DDPM with learned variance, kind of blurry compared to K1. Second-order GM solvers also gave sharper results with fewer outliers than first order.
Okay, compelling on the toy problem. And the main event, ImageNet 256 by 256. How did they set that up?
They used a big diffusion transformer, DITXL2, as the backbone, adapted it slightly. GMFlow DIT predicts the pixel-wise mixture weights, AC, and means RIC, and a tiny MLP predicts the shared variance, SS. Minimal parameter increase, they said. And importantly, used orthogonal projection for all methods.
The evaluation metrics, FID, IS.
Yep, the usual suspects. FID for overall quality and diversity, IS for quality and separability, but they really focused on precision and recall, too. Precision measures perceptual quality, especially important at high CFG scales. Recall measures diversity, and they added their own saturation metric to quantify that artifact issue.
And how did GMFlow perform against the flow BD lines with fancy solvers like DPM+, +Q, UniPC, etc.?
Really, really well. The headline result is precision. GMFlow consistently got much better precision scores across different sampling speeds, NFEs, for both SDE and ODE. GMOD2 hit high precision in just 6 steps. GMSDE2 set a new state-of-the-art precision at 32 steps.
Wow. And FID.
Strong FID too, often better than baselines at low NFEs and very competitive overall. The precision recall curves looked great for GMFlow, showing a better trade-off.
And the saturation. Did probabilistic guidance work?
It did. The saturation metric showed GMFlow images were much closer to real ImageNet data in terms of saturation, especially compared to baselines at high guidance scales. The generated images just looked more natural.
What about the impact of K, the number of components on ImageNet?
Similar trend to the 2D case. More components generally helped, especially for few-step sampling. Performance seemed to saturate around K8 for FID and precision. Interestingly, beyond K8, precision sometimes dips slightly with GMSDE2, maybe due to numerical issues with spectral sampling when K gets very large. They also showed NLL improves steadily with K, meaning the model fit the data better.
And the Ablation Studies. What was critical?
Lots of good insights there. Spectral sampling, vital for good. FID, spatial coherence. Probabilistic guidance, crucial. Swapping it for standard CFG tanked precision and increased saturation. GMSDE2 beat a comparable standard SDE solver. Transition loss helped stability. And the substeps in GMODE2 were necessary for its good performance. Oh, and importantly, the inference time overhead compared to vanilla flow matching was minimal.
So it really seems like the whole package works together. Did they connect it much to other related work? Like variance learning or distillation?
They did briefly. They noted that learning variance in diffusion is kind of like GMFlow with K1. They distinguished it from methods fitting GMs using moments. They acknowledged distillation makes things fast, but it's limited by the teacher model. And they positioned probabilistic guidance as a distinct, more robust alternative to other CFG refinements. They also mentioned GMs being used in GANs and autoregressive models, but often differently, like in the latent space.
Okay, pulling it all together. For our technical audience, what are the absolute key takeaways from GMFlow?
I'd say, first, the power of using Gaussian mixtures to model those denoising distributions more accurately. It's just more flexible. Second, this directly enables faster, higher quality generation, especially with few steps, thanks to the specialized GMSD ODE solvers. Third, probabilistic guidance is a really effective, more principled way to handle conditional generation and mitigate oversaturation.
And the core innovation setting it apart.
It really comes down to 1, the GM parameterization for flow velocity itself. 2, the derived analytic solvers, GMSD-ODD. And 3, the probabilistic guidance mechanism.
And the ImageNet results, especially that state-of-the-art precision with few steps, seem to strongly back that up.
Absolutely. Reducing steps while maintaining or even improving quality, particularly perceptual quality like precision, and fixing the saturation issue, that's a big deal.
They mentioned pixel-wise factorization as a limitation. Where could future work go from here?
Well, tackling that factorization is one avenue, exploring ways to model dependencies across pixels more directly within the GMFlow framework. Using GMFlow as a prior for tasks like Bayesian inference or posterior sampling seems promising too, given the NLL results. And of course, applying it to other data types, audio, 3D, video sequences. Lots of potential.
Definitely fascinating stuff. It leaves you thinking, doesn't it? Given the trade-off, more mixture components, K gives potentially better results but cost more compute? How do you find the sweet spot? What's the optimal strategy for deploying something like GMFlow in the real world, where you have tight latency budgets or specific hardware constraints?
Yeah.
That's definitely something for listeners to chew on as they explore GMFlow further. Thanks, this was a great deep dive.
My pleasure. Always fun to unpack these papers.